In section 4, we're going to start taking a look at the idea of direct proof. And there's actually multiple types of direct proofs that we're going to be looking at in this section, but we're going to start off with the easiest type. And we're going to start off with the idea of how we can prove sort of universal statements using integer values. Now, direct proof is usually a pretty taxing way of being able to prove our universal statement where we have infinite domains. So, and we'll take a look at several examples of this as we go along. But before we do that, we have to make sure that we understand several different definitions. So let's say, for example, we have two integers, n and k. An even integer is of anything of the form n equals 2k. So if we can write any sort of number in 2 times another integer, or an integer is 2 times another integer, it's even. An odd integer for our purposes is going to be n equals 2 times an integer plus 1. A perfect square is going to be such that there's a value, an integer that you can square to find the first integer. And then there's this property of integer closure. And integer closure means that if you add, subtract, or multiply any integers together, then the output's an integer. Okay, so for instance, if I have 2 times 5, which are both integers, that's 10. If I have 3 plus 7, and if I have 17 minus 12, all right? Notice that division is not closed. For instance, 5 over 2 is equal to 2.5, which is not an integer, all right? So that's not closed under integer division, but addition, subtraction, multiplication are. Right? So, and we're just going to assume that that's true for every integer or any pair of integers. Before we go through and do any formal direct proofs, let's just go through and show that some statements may or may not be true. First of all, we want to verify that 37 is odd, which is true because 37 is equal to 2 times 18 plus 1. And that's of the form 2k plus 1. So this is odd since it fits the form 2k plus 1. 2x plus 4 is even for all integers x. We can factor it too, and we would be left with x plus 2. And remember this integer closure, that if we add two integers, then we get another integer. So for instance, this x plus 2 can be written as another integer, let's call it k. So we can say that this is going to be the same as 2k, where k is an element of the integers. And in parentheses, if we really wanted to, we could say k is equal to x plus 2. And what does that mean? Well, that means that 2x plus 4 is even because it fits the very definition of even. Remember, we said that if we can write something in the form 2k, which is this form right here, then it's going to be even. Okay, so this is even since it fits 2k. And then finally, we have this other one, 6y plus 8x plus 7. Now, this is a sneaky one because we're going to have to do something that we might not think to do to be able to verify that this is indeed odd for all integers. So let's rewrite this as 6y plus 8x plus 6 plus 1, right? And I think everybody can clearly see that 7 is the same thing as 6 plus 1. And you might be asking, well, why not say 7 is 3 plus 4 or negative 1 plus 8? Well, the reason we want to write it like that is because we can factor it too, and we're left with 3y plus 4x plus 3, and we still have that plus 1 on the outside. And notice that we have addition and multiplication of integers. Okay, so x and y are integers. We define them as such. 3 times an integer is an integer, 4 times an integer is an integer, and then 3 is an integer, and then we add integer, 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 we end up with integer. So we can just rewrite this as k, and so we would end up with the form 2k plus 1. And that's the very definition of what odd is. And is equal to 2k plus 1, right? So that's what we're trying to do, is we're trying to make it fit the form of either an even or an odd integer. And so we can say that this is odd since it fits the form 2k plus 1. All right. Now, these are not proofs, these are just showing. In the next example, we're going to take a look at a specific proof. Okay, so the first thing we have to do is we have to learn the general steps to a direct proof. And direct proof has 3 steps to it, really. So we're going to define all the variables and use our definitions. So remember, we have a definition of even, which is 2k, definition of odd, which is 2k plus 1, perfect square, where n is equal to k squared, those sorts of things. All right. Later on, we're going to get more definitions. This is probably the most difficult part, is using the algebraic manipulatives, and we have to justify each step. And then the last thing we're going to do is we're going to close out the proof by basically encompassing what we've done. All right, now let's start off with a really basic example of this. We want to prove that for all xy in z odd, so in other words, x is an odd and y is an odd, that the product of two odds is odd. All right, so in reality, we want to prove the product of two odds is odd. All right, so here's how we're going to start this. All right, so let's first of all, step 1, define the integers that we need and define the variables. And we only need 2 variables. Okay, so we're going to say let x and y be elements of z odd. Right, now I'm going to write this in brackets because I've seen this in various textbooks. And for those of you that are going on to take a secondary course in proof, you might have to write this in your other courses. You could say such that x and y are arbitrary but particular. All right. And just to clarify what that means, it means that x and y can be any odd integers, but they can only assume one value at a time. So it's not like a string or an array or anything like that. It's just a single variable or a single value assigned to x and a single value assigned to y. All right. You don't have to write this statement. I'm going to write it each time in orange just to make sure that if for some reason in the future you do have to write it, that you're not docked any points. Since x and y are odd, so thus, by definition of odd, we can say that x is equal to 2k plus 1, and we can say y is equal to 2m plus 1. And you might be thinking, well, why not just say 2k plus 1? Right? Well, that would mean that x is equal to y. And that means that it's only true if x and y are the same integers. And that's not true. Right? So every time we do this, we're just going to use different variables. And of course, we want to make sure that we define what m and k are. Okay, so we're going to say m, comma, k are elements of the integers. So every time we introduce a new variable, we have to go through and we have to define what that variable is, just like in a computer program. Next thing we're going to do, we've defined all the variables. We've used our definitions. Now we're going to manipulate. We need to prove that xy is an odd integer. Okay, so this is step 2. By substitution, xy is going to be equal to 2k plus 1 times 2m plus 1. Right? So all we're doing is we're just substituting back into the original conclusion that xy is an odd integer. Now we're going to do some algebra. Okay, so this is going to be equal to, we're going to FOIL this out, and we're going to get 4km plus 2k plus 2m plus 1. Right? And we have to justify each step. All right, so this is by multiplication. Now, just like we did previously, we need to show that this is odd. So here's the trick that we can do. We can factor out a 2 from these three terms. So that's going to be 2 times 2km plus k plus m plus 1. Okay, and we're going to say that's by factoring. Okay. And then remember that trick that we said about integer closure. So all of this we can say is equal to a new variable. Let's call that variable, let's call it p. Okay, so I'm just going to define this as p, and we still have the 1 that's on the end. Okay, and we can say this is valid by integer closure, but we have to define p as an integer. Right? And again, anytime we introduce a new variable, we have to define it as such a variable. And we're going to say this is by integer closure. And if you wanted to, you can say where p is equal to 2km plus k plus m, right? Because what we did was we just substituted there. All right, now look what we have. We have the very definition of what odd is, right? So now we can go through, we can start step 3, right? So we've done all the algebra necessary. So step 3, we could say hence by above, xy is equal to 2p plus 1. Right, so can't we see that right here? We have xy, and eventually by transitivity, by equal, it's equal to 2p plus 1. So we can say hence by above, xy is equal to 2p plus 1, which is odd by the definition of odd. Right? And then finally, what we can say, hence, for all x comma y in z odd, xy is in z odd. Right? And that's our concluding statement. Right? Whenever we draft a proof, it's self-contained, meaning that we don't have to go outside of the proof to be able to resurrect any sort of ancillary proofs or anything of that nature. All right, so completely new for most of you. All right, so this is the first time that many of you have ever been introduced to formal proof. So a suggestion might be to maybe watch this video again, make sure you understand the key components, especially in the direct proof. And then as we go along, when we start to increase the complexity of the algebra, make sure that you understand your 3 steps.